One of the main topics this year will be the titration of acids and bases. An acid-base titration is a technique where one can determine the concentration of an unknown acid or base solution by neutralizing it with the acid or base of a known concentration. This allows for the quantitative analysis of the concentration of an unknown acid or base solution. Based on the Arrhenius theory, acids contain H plus ions while bases contain OH minus ions. For example, strong acid HCl, when dissociated in water, is separated into H plus ions and Cl minus ions, whereas strong base NaOH, when dissolved in water, is separated into Na plus ions and OH minus ions. The H plus ions from the acid and the OH minus ions from the base will then combine into the water to create even more H2O, which is modeled by this formula. When working with numbers that involve titrations, a common aspect of the calculations have to do with the equivalence point. The equivalence point of any titration with the strong acid and strong base is the point at which the pH is equal to 7. In other words, this is where all the H plus or OH minus ions have reacted with each other to form water, and in other words, are neutralized. The pH of H2O is 7, and this is where we get the equivalence point from. The equation that we used for calculating the molarity or volume required to get the equivalence point in an acid-base titration is M1V1 is equal to M2V2, where M is the molarity and V is the volume. On one side of the equation is molarity and volume of the acid. Let's make that the left side, while the other side is the molarity and volume of the base. In our example, we'll make that the right side. The steps are quite simple. You'll always be given the molarity and volume of one of your substances. As for the other substance though, you'll only be given one, either the volume or the molarity. We plug these values into the equation M1V1 equals M2V2 to find the missing value. In the end, we just want the total moles of H plus to equal the total moles of OH minus. The most common way of titration is carrying out a chemical reaction between two solutions by the controlled addition of a burette from one solution into the other. An indicator or pH meter must be used in the titration to locate the equivalence point. When titrating, an acid could either be added to a base or a base can be added to an acid. Both will result in the same equivalence point, as they both consume each other until neither reactant is in excess, which leaves us at an equivalence point of 7. Let's see an example.
If we have a solution of HCl with a concentration of 1 molar and a volume of 20 milliliters, how many milliliters of 0.5 molar NaOH do we need to add to reach the equivalence point? We first begin by organizing what information we have been given. We know that the concentration of our acid is 1 molar, and we know that the volume of our acid is 20 milliliters. We also know that the concentrations of NaOH that we will be using to titrate the HCl is 0.5 molar. Plugging these values into the equation and doing a little algebra, we can see that the volume required to reach the equivalence point is 40 milliliters, and that's our final answer. That was pretty easy. How about we do a tougher example? What if we start with 50 milliliters of an unknown concentration of HCl and added 350 milliliters of 0.01 molar NaOH to reach the equivalence point? This is still pretty easy because all you have to do is some simple algebra. Let's plug in the information we have into M1V1 equals M2V2, and this time we can show how you can use milliliters the whole way. All you have to do is solve for x, and now you have your unknown acid concentration, which in this case is 0.07 molar, our final answer. How about we go one step further? How many liters of 3.4 molar HCl will be required to reach the equivalence point with 2.1 liters of 2.0 molar LiOH? Once again, let's set up our M1V1 M2V2 equation. After solving for x with a little algebra, we get a volume of about 1.2 liters. So now for a quick recap. We add acid to a base or base to an acid to neutralize it. The reason we are neutralizing it is because the H plus ions from the acid and the OH ions from the bases combine to form water, which has a pH of 7. As more and more of the base or acid gets consumed while reacting with another acid or base, you create more and more water, which should make the pH of the solution get closer to 7. You know the reaction is completed when the pH is 7 because that's when the moles of H plus is equal to the moles of OH minus. We can use this rationale to find unknown concentrations of strong acids and bases.